What if magnetars come near us? Exploring the hypothetical scenario of a magnetar approaching and eventually entering our solar system involves delving into astrophysics, the nature of magnetars, and the potential impacts on our solar system and Earth. What is a magnetar? A magnetar is a type of neutron star with an extremely powerful magnetic field exceeding 10 to the power of 15 Gauss compared to Earth's magnetic field, which is around 0.5 Gauss. Magnetars are formed from the remnants of supernova explosions, particularly from massive stars that collapse into neutron stars. When it comes to their characteristics, magnetars are roughly 20 kilometers in diameter, but with a mass 1.4 times that of the Sun. Their magnetic fields are the strongest known in the universe, strong enough to distort atomic structures. They emit X-rays and gamma rays due to the decay of their magnetic fields. Stages of approach: from 50,000 light-years to entry into the solar system. 50,000 light-years away. This is approximately the distance to the center of our galaxy, the Milky Way. With current technology such as the Hubble Space Telescope and the Chandra X-ray Observatory, we would be able to detect the magnetar's presence through its X-ray and gamma-ray emissions. No immediate effects, as this distance is too vast for any significant gravitational or electromagnetic influence. 10,000 light-years away. As the magnetar moves closer, its radiation might be more detectable, but still no direct physical impact. More detailed observations would allow scientists to study the magnetar's properties, including its rotation period, which is typically in the range of a few seconds. The distance is still too great for significant effects on the solar system. 1,000 light-years away, the magnetar's X-ray and gamma-ray emissions become more prominent, possibly affecting sensitive instruments on Earth and satellites. Increased interest and study of the magnetar due to its proximity. There's potential to learn about the behavior and decay of magnetic fields in such an extreme environment. Still, the gravitational influence is negligible at this distance, though the magnetar's gravitational waves might be detectable with advanced detectors like LIGO or Virgo. 100 light-years away. At this range, the magnetar's radiation might begin to pose a risk to satellite electronics and long-duration space missions. Potential minor effects on the Oort cloud, the distant spherical shell of icy objects surrounding our solar system. Space agencies would likely develop contingency plans for protecting spacecraft and satellites from increased radiation. 5-10 light-years away, the magnetar's X-ray and gamma-ray emissions would become hazardous to human spaceflight and satellite operations. There's a significant radiation hazard. Enhanced study opportunities for magnetic fields and radiation mechanisms would arise. Instruments on Earth and in orbit might experience disruptions. There would also be minor disturbances in the trajectories of outer solar system objects, including Kuiper Belt objects. 1 light-year away. Now we face a severe radiation hazard. The magnetar poses a direct threat to satellites, spacecraft, and potentially even to electronic infrastructure on Earth due to intense electromagnetic pulses, or EMP. Gravitational influence becomes noticeable, particularly on the Oort cloud and possibly the Kuiper Belt, with the potential to perturb the orbits of distant comets. The increased likelihood of geomagnetic storms could affect Earth's magnetosphere, leading to disruptions in communication, navigation systems, and power grids. 7. 0.1 light-year away. Extreme radiation at this proximity could directly affect the Earth's atmosphere, leading to possible atmospheric ionization and increased cancer risks due to high-energy particles. Astrophysical disruptions would be severe, with instruments and satellites potentially suffering damage or becoming inoperative. Earth's atmosphere might experience increased ionization, affecting global communication and climate. Gravitational perturbations would have significant effects on the Kuiper belt and could influence the trajectories of long-period comets and asteroids in the inner solar system. Entering the solar system. The magnetar's intense radiation could lead to catastrophic consequences for life on Earth. Electronic infrastructure might collapse due to continuous EMPs. Massive geomagnetic storms could strip away parts of Earth's atmosphere, leading to global environmental changes. Severe perturbations in planetary orbits could occur, with potential collision threats from disturbed asteroids and comets. If the magnetar enters the inner solar system, its gravitational forces could destabilize planetary orbits, potentially ejecting planets from the solar system or causing collisions. Detailed scenarios and impacts. Radiation impact analysis. Increased radiation would damage electronic components, leading to failures in communication, navigation, and weather satellites. Space agencies might need to develop radiation-hardened technologies or shield existing satellites. High-energy gamma rays and X-rays could ionize the upper atmosphere, disrupting global communication systems like GPS and radio transmissions. There is potential for increased UV radiation reaching the surface, posing a threat to biological life and increasing cancer rates. Space missions would face extreme radiation hazards requiring advanced shielding or mission cancellations. Long-term missions like those to Mars could become unfeasible. Gravitational perturbations could send comets and icy bodies hurtling towards the inner solar system. Increased cometary activity could pose impact threats to Earth and other planets. Disturbances in the outer planets' orbits could cascade inward, leading to shifts in the inner planets' trajectories. Potential ejection of planets from their stable orbits, causing chaotic solar dynamics. Strong tidal forces from the magnetar could affect planetary bodies, potentially leading to increased geological activity like earthquakes and volcanic eruptions. Electromagnetic pulse, EMP, analysis. EMPs from the magnetar could induce massive currents in power lines, leading to widespread electrical failures and blackouts. Critical infrastructures such as hospitals, financial systems, and communication networks could be severely disrupted. The cost of repairing and protecting infrastructure from EMP damage would be enormous. Global economies could face significant downturns due to disruptions in technology-dependent industries. Environmental and biological impacts. Altered atmospheric conditions could lead to changes in global climate patterns, potentially triggering extreme weather events. Ozone layer depletion from increased radiation could exacerbate climate change effects. Increased radiation levels could affect all forms of life, leading to higher mutation rates and potentially causing extinction events for sensitive species. Human health would be directly impacted by increased radiation exposure, necessitating protective measures. Cinematic depiction. The magnetar is first detected by astronomers using advanced telescopes, leading to a global announcement and media frenzy. International teams of scientists and engineers work together to study the magnetar and develop mitigation strategies. Mixed reactions from the public, ranging from panic and doomsday preparations to fascination and curiosity. Governments implement emergency measures to protect infrastructure and prepare for potential disasters. As the magnetar enters the solar system, dramatic events unfold, including massive auroras, satellite failures, and unprecedented natural disasters. Humanity's efforts to adapt and survive in the face of overwhelming odds, showcasing ingenuity, bravery, and solidarity. Conclusion. The approach of a magnetar towards the solar system presents a fascinating yet terrifying scenario. Its impact would span from subtle astrophysical changes to potentially civilization-ending events, involving complex interactions between radiation, gravitational forces, and electromagnetic phenomena. The scientific community would have an unparalleled opportunity to study extreme physics, while humanity would face profound challenges in mitigating and surviving the ensuing disruptions. This hypothetical journey from distant space into the heart of our solar system captures the imagination and underscores the delicate balance of our cosmic existence.